How's it going, guys? Today in this video, we're going to be going over module 12, 12.1 and 12.2, well, the beginning of 12.2 anyway, where we'll be talking about radical expressions, rational exponents, and properties of rational exponents. So we're going to start with defining rational exponents in terms of roots. So the number a is the nth root of a number b if a to the n equals b. So we know what a square root looks like, and we know what cube roots look like. So in general, the nth root of a number will look like this over here. That's what the nth root of a number will look like when we write it out, where n is the index and b is the radical. And we have a little diagram right here in the top right corner of what it'll look like. You have your index labeled and your radical labeled. So something to take note of is that if you have a number that has more than one real root, the radical sign will indicate only the principal or the positive root. So a rational exponent is an exponent that can be expressed as m over n. A rational number is any number that can be expressed as a fraction. A rational exponent will be an exponent that can be expressed as a fraction as well. So let's go down below here where we have this table. And on this table, what it's going to tell us how we translate between a radical expression and a rational exponent. So in the first row, we see that the exponent m over m indicates the nth root of the power, nth power of the nth root of the quantity. So if we have 27 to the third, we can rewrite this as the cube root of 27 all raised to the second power, right? One way to look at it is that the top of the exponent, that's going to be your power. And the bottom of your exponent, or the 3 right here, that's going to be your roots. So when I'm doing problems like this, how I like to think about it is I like to think of power over root of the exponent. When you have a rational exponent, the top number will give you your power, the bottom number of the exponent will give you your roots. So that's just one little shorthand that I think of when I'm trying to write these out. It helps me out. That's how the setup of an exponent will be. It will be power over the root. So back on the first column, we can solve this out now. So the cube root of 27 is 3, and 3 squared gives us 9, right? So that's how we solve a rational exponent. And if you want it in algebraic terms, a raised to the nth power is going to give you the nth roots, or a to the nth root raised to the m power. So like I said before, the n on the top gives you your power, and the n on the bottom will give you your roots. In the second row, what it says is that the exponent m over n indicates the nth root of the nth power of a quantity. So really what the difference between these two rows is just that it's trying to show you that it doesn't matter if you put your exponent or your power, inside the radical or outside of it. So we see here, what it says there is we have 4 to 3 over 2. That equals the cube root, the square root of 4 cubed, which equals 64, or the square root of 64, which is 8. So in this case, we have our exponent underneath the radical. But we could also write it as 4 to the 3 over 2 equals the square root of 4 to the third power. The square root of 4 is 2, so we have 2 to the third power, which is also 8. So what that second row is basically trying to tell you is that you can put your exponent underneath the radical or outside of it, or your power. It doesn't matter where you put it, you'll get the same answer regardless. Well, I don't want to say it doesn't matter. You'll get the same answer regardless, but where you put the exponent can make the problem much easier or much harder. So you have to be able to know where to put the exponent to make solving the problem or simplifying the problem easier than it can be. So let's go on and do some examples. On example 1, on problem 1, what we're told to do is we want to translate radical expressions into expressions of rational exponents and vice versa. So if you have a radical expression, we're going to make it a rational exponent, and if you have a rational exponent, we're going to change it into a radical expression. So, and when we do that, we want to simplify it as much as we can. So on number 1, we have negative 125 raised to the 4 over 3. So one way we could write this is negative 125, all of it raised to the fourth power, and with the third root of all of that. So when we look at it like this, it's a pretty difficult problem, right? Trying to find the fourth power of negative 125 is going to be difficult as it is, and then we need to find the third root of that. That's a lot of work. That's going to be very difficult. It's going to be pretty impossible to do without a calculator. So another way we could write this to make it easier is we could write it as negative 125, the cube root of that, all raised to the fourth power. It's the same exact thing, but we put the exponent or the power on the outside of the radical. And here is a little easier to solve. The cube root of negative 125 is going to be negative 5. Negative 5 to the third power is going to give you negative 125. So that means the cube root of negative 125 is negative 5. And we want all that raised to the fourth power. And negative 5 raised to the fourth power, that's just going to give you a positive 625. If you did it the other way instead with the calculator, you would have gotten the same 625. But this way here is just much easier. It's easier to work with, and it gives you much smaller numbers, so it's easier to solve. So that's why you want to be able to play with the exponent or the power to make your life easier when you're trying to solve these problems. On number 2, we have x to the 11th over 8. So we can rewrite this as the 8th root. Right at the bottom of the exponent is our roots of x to the 11th. So we're taking the 8th root of x to the 11th. So what that means is we need to take out groups of 8 x's to pull out into the front. So it's the same thing we do with square roots and cube roots. We're taking out groups of 2 or groups of 3. We're taking groups of whatever the root is. So we take out a group of 8 x's from x to the 11th. We'll have one group that we can pull out, and we'll be left with 3 x's on the inside. Another way to think about this is that the 8th root of x to the 11th is the same thing as this. 10, 11. All right, it's the same exact thing as this. X to the 11th power is the same thing as multiplying x 11 times, right? So what we want to do now is we want to take out groups of 8 into the front to simplify this expression out. So we have one group of 8 right here, so we can take out 1x. You have a group of 8 inside the radical, you take out 1x to the front, so you have one group of 8 x's, and we're left over with these 3 x's right there, or x to the third. And that's how we simplify number 2. And that's why it works that way. For number 3, we have the 5th power, or so the 5th root of x to the 4th power. We can rewrite this as 6, 4 over 5, right? Power over exponent. So 4 over 5. We can't really reduce this anymore from here, so we'll just leave it as is. And for number 4, it's the same thing. It's going to be power over exponent, power over roots. So it becomes x to the 3 over 4. You can't really reduce this anymore from here. So that's going to be our simplified version and how we switch a radical expression into a rational exponent. So let's keep on going. All right, on this page here, we're talking about modeling with power functions. So what a power function is, it's really just any function that has a power of a variable. So think of the area of a circle, which is the pi r squared. The r squared makes it into a power function. It's a product of numbers that has a power of a variable. We also have the volume of a sphere, which is, I believe, 4 over 3 pi r cubed. It's something like that, but the point is, you have an r cubed somewhere in the formula, and that's what turns that equation into a power function. So basically what we're saying is that power function will always be in the form y equals ax to the b power, where a is a real number and b is a rational number. So a power function will just be a product of numbers, a product of real numbers, and a variable raised to some rational number. So example 2, we have this biology problem, and we're told the function r equals 73.3 times the 4th root of m cubed, and that this right here, that 4th root of m cubed, that's what turns this function into a power function. And that function is known as Kleiber's law, and that relates to the basal metabolic rate R in calories per day burned, and the body mass M of a mammal in kilograms. This table below shows the typical body masses for some members of the cat family. And what we're going to do is we're going to want to fill out this table, and then we're going to answer letters A, B, and C. So how we're going to figure this out is that our masses right here, these are all our M values that we're going to take and plug into this formula here. And when we do, we'll get our metabolic rate for each mammal, and then we'll go on and solve the problem. So for a house cat, the typical mass is 4.5 kilograms. If you plug that into the equation, we get 250 calories. For a cheetah, its typical body mass will be about 55 kilograms. You plug it into the equation. When you do, you should get 1,500 calories. And for a lion, its typical body mass is 170 kilograms. So if you take it and plug it into the equation, you should get 3,450 when you round to the nearest 50 calories. So we filled out our table. We know what the typical metabolic rate will be for a house cat, cheetah, and lion. So what we're going to do now is we're going to rewrite the formula with irrational exponents. So our our function is R equals 73.3 times the 4th root of m to the 3rd power. So to rewrite this as a rational exponent, we need to change that part right there into a rational exponent. And remember, it's going to be power over root. So that's what our formula will be with irrational exponents. And written a little nicer is right there underneath the little blank. R equals 73.3 m to the 3 over 4. That's what we get when we rewrite the formula with a rational exponent. We change the radical expression part of it into a rational exponent, and that will give us our formula with a rational exponent. On B, we're asked what is the value of R for a cheetah to the nearest 50 calories. Remember, R is the basal metabolic rate. We already solved that out, and we got 1,500 for cheetah. And lastly, on C, we're told that from the table, the mass of a lion is about 38 times that of a house cat. So a lion is about 38 times heavier than a typical house cat. And we're asked, is the lion's metabolic rate more or less than 38 times the cat's rate? So you want to see if the lion's metabolic rate is also 38 times bigger than the house cat's metabolic rate. So what we're going to do is we're going to set up a ratio. And the ratio will be 3,450 over 250, or the lion's metabolic rate over the house cat's metabolic rate. And we solve that out, we get 13.8. That 13.8 is less than 38, so we know that the lion's metabolic rate is less than 38 times the cat's rate. So all we really did was fill out this table, and we used the table to answer A, B, and C. So on to page 5 here. On this page, what we're going to do is we're going to fill out all the properties of rational exponents. So the first property that we have is the product of powers property. And what that says is that if you have two powers with the same base, and you're multiplying them together, you just add the exponents. For instance, if we have 12 all to the 3rd power, and we multiply that with 12, let's say to the 2nd power, we add those together. When you multiply these two together, we get 12 to the 3 plus 2. Our bases are the same, and you're multiplying them together, so you add the exponents, so we get 12 to the 3 plus 2, or really just 12 to the 5th. In algebraic terms, this will be a to the m times a to the n will equal a to the m plus n. You multiply two powers with the same base, you can add the exponents. The quotient of powers for the quotient of powers property, what that says is pretty much kind of like the opposite of the product of powers property. So if we're dividing two powers with the same base, we subtract the exponents. So if we have 12 to the third divided by 12 squared, the base of 12 is the same for the top and the bottom. So that means when we're trying to reduce this, we can rewrite it as 12 to the 3 minus 2, or just 12 to the first power, which is just 12. So if you're dividing two powers with the same base, all you have to do is subtract the exponents from the top and the bottom, and you get your simplified version. Algebraically, a to the m all over a to the n will give you a to the m minus n. So for powers of a power property, this is talking about when you have a power and you're raising it to another power. All you do is multiply the two powers together. So if we have 12, say, squared to the fourth power, you multiply 2 and 4 together to give you 12 to the 8. Because it's 12 squared happening 4 times, so it's going to be 12 to the 8th power. Algebraically, we can write it as a to the m raised to the nth power. You multiply both your exponents together, or both your powers, to give you a to the m times n. Next, we have powers of a product property. So to find the power of a product property, all we do is distribute the exponents. So let's say we have 12x, all raised to the second power. We can rewrite this as 12 squared times x squared. And we know that's true as well, since 12x times 12x is 144x squared, which is exactly what we have here. 12 squared is 144. So if you have a product and the whole product is raised to an exponent, you can distribute that exponent out. And that's what it says here in the algebraic way. If you have a product of AB raised to the m power, you distribute that m to the a and to the b. Next, we have the power of a quotient property. To find the power of a quotient, we're going to distribute the exponents. So it's very similar to the power of a product property. So if we have 12 over x, all to the second power, we can rewrite this as 12 squared all over x squared. We can distribute the 2, or the exponent, sorry, to the top and the bottom. And we know this is true since 12 over x all squared is 12 over x times 12 over x, which will give you 144 over x squared, which is what we got. So algebraically, it's a over b raised to the m power equals am over bm. So if you have a quotient all raised to a exponent, distribute the exponent to the top and to the bottom. The power of 0, what the power of 0 says is that if you have any real non-zero number raised to the 0 power, you always get 1. So basically, any real number you put, let's say 12 raised to the 0 power, that's going to be 1. If we have negative 12 raised to the 0 power, that's also going to be 1. Any number that is not equal to 0, if raised to the 0 power, will give you 1. And that's what it says right here. A to the 0 power equals 1 if a doesn't equal 0. And right here on the negative exponents, what this says is that if you ever have a negative exponent, you just flip it to the other side of the fraction to get a positive exponent. So let's say we have 12 to the negative 2. We can rewrite this as 1 over 12 squared. And same thing if you have 1 over 12 to the negative 2, that's going to give us a positive 12 squared. All you do is take the base, move it to the top of the exponent, and change the exponent from a negative to a positive. You don't do anything other than that. You just move the base to the other side of the fraction and change the negative into a positive. And algebraically is what it says here. We have a to the negative 1. It's a little hard to see. A to the negative 1 will equal 1 all over a. Just move the exponent to the, sorry, not the exponent, but the base to the other side of the fraction. Change the exponent into a positive. So that's it for the notes. But I do want to go over the first 2 problems of the homework to kind of give you a little better reference of how we solve these problems. So these problems right here are very similar to the ones we did earlier. We want to change these problems from rational exponents to radical expressions, and radical expressions to rational exponents. So for number 1, we have 81 over 16 raised to the 3 over 4 power. So we're going to use that rule we just learned, where we distribute the exponent to the top and to the bottom. So we have 81, 3 to the 4th power, all over 16 to the 3 over 4 power. Next, we're going to rewrite this as radical expressions. So we can write it as 81 to the 4th power, all cubed. And the same thing on the bottom, to the 4th power, all cubed. In this case, we want to write the exponent on the outside because we can figure out what the 4th root of 81 is going to be. And same thing with the bottom, we can figure out what the 4th root of 16 is going to be as well. So the 4th root of 81, or what raised to the 4th power gives you 81, that's going to be 3. 3 to the 4th power gives you 81. So we're left with 3 cubed on the top. And on the bottom, we have 16, the 4th root is 16. So what to the 4th power gives you 16? That's going to be 2. 2 to the 4th power gives you 16. So we're left with 2 to the 3rd on the bottom. We just need to work this out. 3 to the 3rd power is 27. And 2 to the 3rd is 8. And that's going to be our simplified version of number 1. And now for number 2, we have xy all raised to the 5 to the 3rd power. So we're going to work this out as well. We want to change this rational exponent to a radical expression. So we can rewrite this as xy all to the 5th power and the 3rd root of all of that. In this case, we want the exponent inside because we can reduce this by taking out groups of xy's, right? We have 5 groups of xy's underneath the square root, or underneath the radical. So we take out one group of 3 of those. And when we do, we're left with 2 groups on the inside. You can't reduce it anymore from here, so that's going to be our answer. I'm going to leave number 3 and number 4 for you guys to do on your own, as well as the last problem on the homework. One thing I want to clear up is that the equation right here should say 241m to the negative 1 over 4. It's a little hard to see, but it's negative 1/4. So anyway, guys, hopefully this video helped. And I'll leave the rest of the homework for you guys to do on your own.